Good evening. It is late o'clock here for the Advanced Science Academy. We are doing, let's see, today is the 14th of December in the year of our Lord, 2021. And we are doing a paper where the senior author, Mark Baer, looking to see if I have his textbook. The senior author, Mark Baer, is your great grand mentor. He trained my postdoctoral advisor. While he was at Brown. He's no longer at Brown. I think he's at MIT now. And so this is correction of amblyopia in cats and mice after the critical period. And if you're into developmental neuro like me, this is a weird thing because this is a classic Nobel Prize winning thing that was found called the critical period. And so it's a big deal. And so Nolan's going to go over that. Remember also the rules that here in the Advanced Science Academy, where we are learning to communicate, we do so face-to-face as much as possible. Please turn on your cameras. Both Nolans should have their cameras on. If you notice, Nolan actually has two accounts in here. So, so Nolan, if you share from the other account, you're gonna have to. We all are going to have to pin it. We'll see. Whatever comes up with the slideshow, that's what should be pinned. I want to wait until everybody's up here. Come on. You should. I don't want to see the bottom, the top of your head. Mine is nice and shiny. I just shaved it. But you should be face in the middle. Let's look professional here. Ideally, I would make one of these little things down for you guys, but I'd have to be convinced that the effort is worth it. Okay, without further ado, go ahead, Nolan.
Alrighty, okay. So Dr. Char already said the title, and so hopefully you kind of know what it's about, like a little bit already. So I'm just gonna put this up, and okay, so it is correction of amblyopia in cats and mice after the critical period. And so amblyopia is like lazy eye, So the critical period is when it classically would be treatable under normal circumstances. So usually with brain development, there's only a certain window of time when you can treat it before it is kind of too late for the brain to change enough to kind of see again. So slide 2, can you see it? Can you see it? Okay. So really it kind of all comes down to ocular dominance columns and the optic nerve. So after light is converted to electrical impulses, it's sent through the optic nerve, and that's how it gets to the occipital lobe to be processed. So when the optic nerve is being developed in kids, like the neurons will have lots and lots of synapses, but as the brain develops, only really the useful ones will be kept, and then the other ones will be eliminated. And so the useful ones will form ocular dominance columns, as one eye will, kind of dominate a control of like visual input going to a specific spot. Not necessarily uneven if there's no monocular deprivation, but specific input will go on specific paths to specific places to be processed. So in like the typical human, the central vision will be processed on the same side of the brain that the eye that sees the input is on, and then peripheral vision will be processed on the opposite side, which is the contralateral side to the eye. And so it crosses and it goes to different places. So you can see how if there's like a problem in development, there can be a problem in being able to actually process the vision. And so lazy eye may not seem like a huge thing, but if you think in terms of concussions, which is a really good example Dr. Char mentioned, is that if you know, like knock your head into a locker and then all of a sudden you don't have peripheral vision anymore, you have tunnel vision, that's because your impulses can no longer cross the optic chiasm. And because they can't do that, they can't be processed in the opposite side of the brain. And so they're not processed at all. And so, you know, that problem with kind of the optic nerve can affect your sight. And then when it comes to amblyopia, that's more developmental. So, for instance, if you're a kid and your eye gets like a cataract, then that eye is blocked. It's not seeing as well. It's not really, you know, taking as much input and then processing it. So it's less effective than the other eye. So the other eye will become more dominant in taking in input and then processing it. And so because it's more stimulated, the optic nerve will develop in favor of that eye. And so then even if you get the cataract removed in the other eye, the affected eye still just won't work as well because the brain isn't wired to let it work at that point. So when it really comes to amblyopia, that would be deprivation amblyopia. There are some other types where, you know, there's less of a disparity between the affected eye and the non-affected eye, but standard treatments would be eye patches. When you see those kids like wearing eye patches, that's on the eye that does work. And so what that's supposed to do is like block the working eye from getting input and like taking over the nerve and everything in there, so that the other eye can take input and process input, you know, without being with the ability to, you know, have some control. But of course, after a certain period of time, you know, when you're an adult brain, there's less of an opportunity to really rewire that. But what these researchers found is that in the past, some people who have had to get their working eye removed, or it stopped working altogether, just like unrelated, then their vision in the amblyopic eye was actually fully restored. So in this experiment, as you know, what they wanted to do was mimic that and temporarily inactivate the eye that did work completely. And so, but be able to bring it back and have both eyes work. So what they did was they injected tetrodotoxin into the retina of the working eye, and that's a sodium gate blocker. So that prevented any impulses being sent off from the working eye to through the nerve to the occipital lobe, completely inactive for a very short period of time, and that just in that small window, like a day or two, the other eye would be able to start working again. So that's really what we see as we head into figure 1. Actually, before we start, any questions so far? Was that clear?
I want to just clarify what the result of amblyopia is. Like you've likened it to lazy eye. And my only issue with that is that there are different colloquial versions of what somebody calls lazy eye. Like sometimes you meet somebody who is like this. Hey, how you doing? People call that a lazy eye. Sometimes if it stays in one place, but your other eye moves around, some people call that lazy eye. Amblyopia is its own thing where it's actually about the vision, not so much about the look of the eye.
True, yes.
So what if you have amblyopia, what do you expect?
You're not like processing vision from
So
that eye.
So what is the perception you have?
From your other eye.
Okay, but if I block the good eye and I look out,
Mm-hmm.
through the amblyopic eye, what's the sensation I'm getting? Do I see things?
I believe that you can process light to some extent because what they show is that, right after monocular deprivation, there is some visual evoked potential, but it's not, full. It's not where it should be.
Mm-hmm.
And then once it
So,
recovers, it gets to where it should be.
okay, so I think an easy way to say it is that your vision is not acute and it's not refined, but you do have vision, right? And so it's very, very blurry. And I don't know if you're going to mention this later, so shut me up if I'm ruining anything. But if you ever see kids, really young kids, who have like Coke bottle glasses, super, super thick glasses, because they have really poor vision, a lot of times that's because their eyesight their brain sight had not developed correctly for various reasons, which no one might get into. Okay, that's
okay.
it.
Okay, so figure one. Figure one is really neither eye has been monocularly deprived. Both of them work. They're just showing the effect of the TTX when you inject it. And so to explain this, I'm going to pass this to Campbell.
And Campbell, did you have a question? You raised your hand.
Yeah, isn't TTX from pufferfish?
It is.
Yes.
Okay.
Yeah.
I just thought of that.
Cool thing about tetrodotoxin is it's also used in oh geez, now the name of the culture is slipping my.
Wait, it's like the zombie people, right?
Yeah, zombie people. Wait, is Johan here? Because it's actually the French Crete. No, what are they called? Cajun, the down in Haiti, Louisiana, that type of area. We've Johan and I have actually talked about it in the past. But yeah, you can. First of all, it's deadly. Don't drink it. That's why pufferfish takes 6 years of training, I think, to use it for sushi. Because if you mess up a little bit, will kill you. But if it's really, really diluted, you can turn people essentially into zombies. They will respond to your suggestion. Okay, go ahead.
Okay.
Quick side note. That toxin is also used as a
Don't complete that sentence. As you're standing in a bakery, I don't want to hear where it's also used, because you're going to be like,
No,
we also use it in our baked goods.
Just in my kitchen.
No, it's used also for oftentimes it's used in like the Central American countries as some sort of sleeping drug.
Yeah, it'll put you to sleep permanently.
Okay, am I good to go?
Yeah.
Okay. So, letter A pretty much is just showing you how the contra eye and the ipsi eye, primarily the contra eye, how it crosses over and it's controlled. Well, it's like images are, what's the word I'm thinking of? I don't know. Well, it's processed on the opposite side of the brain, and it also shows that the TTX was injected at that location, which is V1B. And then B pretty much shows the time frame of all of this. So the ipsi eye obviously doesn't have TTX. It's the kind of like a control next to it. And then this shows that TTX, it's not permanent and that it wears away, and that over time, like after 2 days about, it's kind of like almost fully functional again. And so when TTX is injected, the retina is inactivated. And so then C and D are probably like the most important figures, I would say. So it's really important to see the baseline of the two eyes. And so the contra eye, the baseline is significantly higher than the non-activated IPSI. And that kind of just shows that the baseline is like more dominant, or not the baseline, the contra eye is more dominant than the IPSI. And then immediately after the TTX was injected, the magnitude of the VEP is significantly lower. And then over time, it is able to like readjust as the TTX wears off. And then if you look at figure D, when it's like 1 hour, it's way higher than the baseline for the IPSI than it was. And that's like very important because it shows that when the contra eye's retina was inactivated, the IPSI was able to kind of take on a new function and work harder. I mean, that's kind of stupid like wording, but it's kind of like when you cut your hand off.
Put it.
What?
I think that's a good way to put it.
Okay. So let's just say I'm right-handed. And so if I were to cut my right hand off, over time, I would obviously become left-handed. So that's kind of how Nolan and I thought of it. It's kind of easier to understand. So when your retina is inactivated on your dominant eye, over time, you're obviously able to like become like better with your left hand. And so therefore your IPSI eye is able to become more dominant.
Okay, so I can see why you would make that argument.
Okay.
But in doing so, I think you're actually, let me get this down. I think you might be missing one of the reasons this is cool. Okay. And I will mention cocaine at some point in this explanation. And Nolan, tell me to shut up if you need me to. But the title of the paper, the title. Let's try this again. The title of the paper is After the Critical Period. I would actually argue with Dr. Bear that then it's not a critical period if it is rescuable at all. A critical period by definition means that we only within that period can the brain plastically learn to do a thing. That's by definition, that's what it means. And so if you're saying that you can restore vision after a certain period, then I would argue, well, then it wasn't a critical period to begin with. It's a sensitive period, which is slightly different. But why is this cool is that in the past, our understanding of critical periods, and again, Nolan, stop me if you're planning on explaining this, but in the past, our understanding of critical periods were severe. Like you either learn it or you don't within the critical period, and then you're screwed. Like afterwards, nothing. It's also when imprinting happens. So if you have a clutch of eggs from a duck and they all hatch and they look at you, they go, oh, mommy, and they imprint on you. But only when they first emerge from the egg. That's called a critical period, right? There's only a certain time in your development when you produce something called dopamine 1 receptors. Okay, so in your brain, dopamine is kind of important. It's how you have fun, et cetera, et cetera. Dopamine 1 receptors are only made in utero while your mother is pregnant with you. You really don't make them ever again the rest of your life, pretty much. And so if your mom does crack, then it causes the levels of your dopamine receptors to actually drop. And then you will never have them again, because that's a true critical period. Now, if they're claiming that they have some way of rescuing, like turning a critical period back on, that would be pretty cool. Is that what they're getting at? Or am I jumping the gun a little?
I think they're really just saying that treatment isn't restricted to the what was previously considered the critical period, because they can do it in a different way than is the traditional treatment.
In a different way, instead of the eye patch.
Yeah.
Interesting. Okay. All right, keep going. I'll shut up now.
Okay. But thank you. Yes. And just to clarify, B1B would be the location of the electrode, the recording electrode that records the visual evoked potential magnitudes, and the injection would go into the retina. But moving along to figure 2, this is kind
I'm
of where,
sorry. Can I say one more thing? I'm sorry.
yeah.
In the brain, mice. This is mice, right? So mice and humans are a bit different in where their visual pathways go. In humans,
Yes.
you got that. All right. So I won't say anything.
Okay. So yes,
I was
it's
going to
we
draw
can
it.
definitely see it in this figure. So if you take a look and compare B and C, compare the sham groups. That is pretty much the sham groups will be at the baseline for visual evoked potentials all throughout the experiment. So once again, you see how the baseline for the contralateral eye is much higher than that for the ipsilateral eye, and so that's because the way that mouse's like impulses are sent, most of their vision is processed contralaterally to the eye that receives the input. Unlike humans who are about 50-50. So like in your right eye, half of what your right eye sees, like the central vision, will stay on that side of the brain, and then half of it, or the peripheral part, will go to the other side of the brain. So that accounts for the difference between the mice. But then that kind of explains part of why cats are brought into this experiment, because cats, like the orientation of how they process vision from each eye is much more similar to humans. So you can see they kind of looked at it a different way when the cats came in. But for figure 2, this is when monocular deprivation does come into the picture. So I don't think Shannon's here, so I will do this one. So A is very similar to the previous A. It shows where the electrode is placed. It shows the contra eye, which is the one that is monocularly deprived, and it shows the eye that is ipsilateral to the electrode, and that is the one that will be injected with TTX. So on the timeline, you can see that beginning at, what is that, postnatal day 26, that's during like the critical period of development. That is when the contralateral eye is monocularly deprived, and that is for 3 weeks until P47. And that point, it is after the critical period, or the so-called critical period has passed. And so then at that point, the eye is opened. They record the visual evoked potential, and then they inject the ipsilateral eye with the TTX. And then the black represents where that eye is like temporarily shut down. And then, vision is restored in both. So then when you get to B, you have 3 groups. You have the sham group, you have the monocular deprivation group, and you have the group that had both monocular deprivation and TTX treatment. So sham group stays at baseline because it's not altered. Monocular deprivation group is much lower because that eye, as we talked about at the beginning, was developed poorly in that, it has very low visual evoked potentials, and because it does not receive the TTX treatment, it does not go up. And then in contrast, the one that does receive the treatment right next to it, you can see the steady increase over the course of the 4 weeks, where it just kind of levels and it's back at the baseline. And then C would be a very similar representation of that. You can see the sham represented with black stays at baseline. MD group stays very low, and the MD and TTX group curves up, levels off. And then D, it shows visual evoked potentials recorded for different spatial frequencies. So when they would test the mice to see what their visual evoked potentials would be, they would, flash images with different spatial frequencies. And so you can see how, like, week 0, for the TTX group, it was very low, but then it shifted up by week 4. And then E through G shows what's going on in the ipsilateral eye. Once again, sham stays the same because it is unaffected. And then for the MD and the MD TTX group, it's interesting because right after the deprived eye is opened, there is a jump in the visual evoked potential magnitude in the ipsilateral eye that they record right before they do the injection. And that's it's an impermanent response to the fact that that the other eye has been deprived. But then once that eye is injected, it will only go back to its baseline because the other eye has risen to what it's supposed to be or has just leveled off, right? And then you can see in F and G, those are essentially the same as C and D, but there's not really the difference because that eye is not monocularly deprived. Any questions?
When you probably, I think you discussed this in figure 4 that you're going to skip B. And I just want to point out that the jumble of unknowable stuff in 4B, when it's processed by the computer, the result is what you see as the waveforms in the top of C, D, F, and G.
Oh,
yeah. I think the word is deconvolves. I think it deconvolves, or it's a deconvolution of all that messy data into that, which is somehow meaningful to people who are smarter than us. Maybe it's meaningful to you. You might be smarter than me. I don't
no.
understand it. Yeah. Okay.
Okay. So now, figure 3 is my favorite. Figure 3, I think, is where it's really the most meaningful because it compares the TTX treatment to the reverse occlusion treatment. So reverse occlusion is what is mimicking the eye patch treatment. They don't use an eye patch. They suture the ipsilateral eye closed, which is really interesting because that's what they did to monocularly deprive the contralateral eye in the first place. And so you can see what effect an eye patch might have on an adult as compared to what the TTX would have. And so just to kind of explain all that, my academic superior, Sienna.
They did this to cats or mice?
This one was still mice.
Okay, that's fine. They can suture mice eyes shut. I don't care about that.
Oh, I certainly don't care about the cats. They could take their eyes out. That's fine with me. Sienna, is Sienna going? Where I don't even see her.
Yeah, here.
Yeah, Sienna, if you don't mind, the first thing I'd like you to do is, because there a lot of this, especially for the freshmen, a lot of this is going to go over their head. So at least every journal club, we want to be able to point out what may be to you the most obvious stuff about a figure, and that to them is brand new. Like, what does P mean in the age? Stuff like that.
Okay.
So freshmen, listen up, because this is how this is how we make our figures and stuff. Go ahead.
Yeah.
She's gonna be
P,
like,
I'm not exactly sure what P means.
Oh, okay.
It's postnatal day.
It is postnatal. Yes, good. That just means like after birth, postnatal, postnatale, right?
Yeah. Okay. So here on the left is the on the left is the two pictures of the brain and the eyes that have been on the past two figures. And to the right of that is the where they either like sewed the eye shut or they put like the injection in it. So the gray represents the monocular deprivation in the contra eye on the top figure, and the black is when the IPSI eye was inactive from the TTX. And so it shows that it was like inactive until like week 1, and then it does its thing, I guess. And so underneath, the location of the electrode and the IPSI eye that was treated in reverse was I'm not exactly sure which figure this is. I think I might have mixed them up.
That's okay. It's really bad when it's actually your figure that you designed and you mix it up in front of people. But this isn't your figure, so it's okay. We all do this.
Yeah. I've done that. I did that.
To your own figure? Because
My-
I'm sure I've done it too, where you're like explaining what you think is your figure for like 20 minutes, and then you look back and you're like, oh crap, that's the wrong figure.
I explained inverse data for my entire master's thesis. Inversed. Flipped.
Yeah. Well, that's appropriate, huh?
So for A, right, the bottom part. Okay. So that bottom part of A, that would just be the eye that was treated with reverse occlusion, which is, you know, the second suture, you know, on the IPSI eye. So that one is also monocularly deprived for the same period, but then following that, instead of having an injection, it is temporarily sutured closed for a week, and then it is opened. And so then that carries on to B. Sienna would be good. Okay.
Yeah. And so in B, you can see at the beginning part, that is where the eye was just like injected and it improved by the 4th week. But in the eye that was sutured shut, it showed a lot better improvement, I'm thinking. It rises in week 2, but then the recovery is not lasting, and instead it like reverts back to its original state. And in C, it shows pretty much the same thing as B, but in a format that's like a line graph, so you can see how the first approach has a much better outcome than the second approach, which the effects don't last. And so in figure D, we can see that at week 1, both have improved, but by the 4th week, the RO group has dropped off and is not anywhere near the other group. And in figure E, both groups rise. You can see rise in week 1, and then the RO group drops off significantly again. Compared to the TTX group, which drops off a little bit, but not as dramatically as the RO group. And figures F and G show pretty much the same thing as E, but in a different format that could be easier to understand.
Yes, awesome. So yeah, you can definitely see the difference between reverse occlusion and the TTX injection. You know, after the first week, the reverse occlusion just stops working anymore. And that just shows how there will be, a very brief response to the treatment, but it won't last because at that point the brain cannot be, changed like that from just that. It has to be totally, the eye has to totally be, inactivated in order for that change to occur, as you see with as is shown by the TTX group.
Freshman, remember yesterday I asked a question. First of all, yesterday morning feels like 3 weeks ago. But yesterday morning I asked a question. I can't remember what the question was, but you guys kept giving me answers that were really superficial. What was the question, AJ?
It was something about why are your bones sore after
Oh no, why
lifting
muscle?
for the first time?
Right, pain. Right, what's causing the pain? You guys kept giving me superficial answers. Along the same lines, when you get data like this, right, and you see that there's an effect after some sort of intervention, the question that should come to mind is a very simple question: why? Like at the molecular level, so we're seeing a difference in spike potential. So at the cellular level, what's happening at the molecular level that's actually causing this? That'd be something you'd want to know, because it's at the molecular level that you actually do any type of pharmacological intervention, drugs and stuff. Are you going to talk about antidepressants?
No, I wasn't planning on it.
Okay.
Because, I mean, if you want to mention what you mentioned, I just didn't feel confident about getting that right to the point where I could fully tie it in.
That's fine. I actually have when you're done, I'll show a slide or two from an animation of how this sort of works in the brain.
Okay.
Okay. Something I did back in 2006 or something like that.
Okay.
Yeah.
So those are the different, treatments that happened with mice, and then you move on to cats with figure 4. So this is interesting because they kind of had a different approach to how they, did the process with the cats. Definitely part of this can be accounted for by the limited number of cats. There were only 10 cats in the whole program, and only 4 of them received the full treatment. So in that sense, they had to be a bit more careful maybe in what they did to make sure they made the most of the available test subjects. So some of these differences will pop up. In fact, the first part A, you can see the cats, the design for how their visual evoked potential was recorded was through an EEG. So it wasn't invasive. They did not have an electrode implanted. And so my thought with that was that they just didn't want to risk an invasive surgery on a cat that they might lose. I feel like EEGs also just could be just as effective. They just work differently. And so the way that it's translated is harder to understand at first. And B shows how they translate the EEG into the measurable visual evoked potential.
It's definitely the second option. It's that they think they can get as much information from a non-invasive approach, because nobody cares about cats. So if the cat dies in the experiment, it's not a big deal because it's a cat. Nobody likes cats. But they can get as much information from EEG. But how do you get them to stay still?
You
put a box out so they sit in it.
I couldn't hear anybody. What?
Said you put a box out so they could sit in it.
I think in methods they may have mentioned the cats were under an amount of anesthesia.
Yeah.
I know that happened at some point. That may have been for the recording process,
Yeah, that's probably what it is.
but
It's yeah.
yeah, okay.
It's
Um,
usually a paralytic, like vecuronium or something.
okay. So yeah, so that covers B. C, that would be another one that kind of touches on the different spatial frequencies, different responses. So you can kind of see that as the cycles per degree increases, there's kind of a decrease in the visual evoked potential. That's not really related to the experiment as a whole, but it shows you the visual evoked potentials, is what the point is. And then D, D is another timeline. So in this one, for the cats, they did left eye is monocularly deprived, right eye gets the injection. And so they started monocular deprivation at postnatal day 30, and like the mice, they did it for 3 weeks. So for cats, that ended at P51. And then instead of going right into the injection, they gave the cats 8 to 10 days with an opened monocularly deprived eye and the ipsilateral eye, or like the right eye, without an injection, because they wanted to get recordings to make sure that the monocular deprivation worked before they went ahead, like, and worked stayed constant, like it was lowered fully. So then after that point, they did do the injection, and this was very different. On the cats, they did 4 to 5 injections of TTX. And so that's interesting, first of all, because they did them spaced out so that the eyes were inactive for 8 to 10 days, and because they said 4 to 5 and 8 to 10 days, because that's a difference between, you know, what each cat may be getting. And so they don't really account for how that changed the results or any differences between each cat. I would hope that that meant that there wasn't a difference depending on how much TTX they used and for how long, but they didn't address that.
Yeah, you know, thinking about it, knowing Mark Bear, what they probably did was they did it separate. There's only 4 cats here. It's only 4 cats. That's a really small number, and they did it. Do the math here. 8 days apart times 5 injections versus, so 8 times 5 is 40, if my math is correct, right? But 10 times 4 is 40. You're still getting the same number of days. And then they probably, knowing him, compared the 8-day protocol versus the 10-day protocol, found there wasn't any significant difference, and so lumped them together, which is fine. That's statistically, that's fine. But I think we're kind of left to just hope that they did it right. Oh, and Campbell keeps raising her hand. She's getting a little obnoxious.
I just have a question.
Mm-hmm.
So, wait, I'm kind of confused. Did they do like the 4 to 5 injections within 8 to 10 days? Or did they like do it multiple times, like one injection?
So it was over the course of 8 to 10 days. So they did one injection and then skipped a day, and then it did another injection and skipped a day and did another injection. And it kind of points it out on the.
Because wait, Char, you were saying Dr. Char.
Yeah,
sorry.
no, my
You were saying-
impression was different. My impression was 8 days injection, let another 8 days go by, injection, versus 10-day injection, 10 days injection, 10 days injection, which is a grand total time. Because I don't, where are you seeing a timeline that's if you look at the P here, left is P 30 to 51, then 8 to 10 days, and then 1 month. I mean, you end up being around. No, you're right. 8 to 10 days. So then everything I just said is wrong. My interpretation completely wrong. I can't trust Mark Bear. I don't know. He'd get mad at me if I said that. I trust him. He's fine. He's a little intimidating. He intimidates me. Okay. Get to the fun part, which is
Okay.
H.
H. H is the fun part. Do you want me to
Why?
skip
What
the other
happened? How'd
ones?
they do this experiment?
Hmm?
How'd they do this experiment? That's the fun part.
How'd they do it?
Yeah.
Oh, they killed the cats.
Shucks. That's terrible. It's only 4 for you cat weirdos. It's only 4 cats, so don't worry.
Well, it was more than 4 because 4 were in the bottom group, and then even more were in the group on top. But it was only 10 total.
I was trying to make them feel better, but
Oh, sorry,
you just
guys,
ruined
sorry,
that.
cat lovers.
All the cat weirdos.
But just to really quickly go through E, it's pretty similar to the other graphical representations before. You see the blue one, that's a monocular deprived. It starts off low because it was monocular deprived. Once the injection happens, it gets higher and then it levels off. And inverse for the eye that gets injected, it starts out high, it gets injected, it goes low, and then it wears off and levels off. Same thing in F. G shows the shifting ocular dominance between during that time period. They start out even when monocular deprivation occurs. It shifts, then it shifts the opposite way because the other eye gets injected, and then they end up even as they're supposed to be. So now you're done with the cats. They kill the cats, and they look at their dorsolateral geniculate nucleus sizes. So
DLGN. We just called DLGN, yeah.
So that's really interesting because in cats and primates, the size of these can be related to monocular deprivation. So when these are smaller, that is an indicator that eye has had monocular deprivation. But when they're the normal size, then it appears that there's not a problem. So H shows the top row. If you look at the middle of the top row, that would be the group that is monocularly deprived but not treated. And so those are small, and right next to it is the non-deprived group. You see how that's bigger. So you can obviously see the smaller DLGN is monocularly deprived. But then when you see the ones right below that were treated, those are the same size as the normal ones. So they were at one point, small because they were monocularly deprived, but then through this process, they were restored to the same size, which is pretty impressive to think about. Poor cats, of course, but
they didn't feel anything.
When you go on to I, that's the deprivation effect. So that's just kind of showing the displacement of the soma sizes in the normal ones, in the monocularly deprived group, and in the MD then TTX group. And you can see normal and the TTX groups are the same, and then the ones that are just monocularly deprived are very different. And then J is not very deeply discussed, so please correct me if I'm wrong. But it's showing how the same soma size for the TTX group and the normal group isn't just caused by chance or degeneration. It just is because of the treatment. They appear the same. At least that's what it does. So that would complete the figure. And so, there were definitely differences between the cats and the mice, but the results stayed the same, is that when they're treated with TTX, there is the improvement. So any questions or comments? on that.
Do you want to see what this looks like?
Sure.
If you guys stop sharing, I know you have to conclude, but stop sharing your screen for a moment, and then you guys pin me. I'm going to transition. So the dorsolateral geniculate nucleus is part of the thalamus. Okay, the thalamus is the very center of your brain that acts like a railway station. It goes and directs things that are coming into the brain and things going out of the brain. So when your eyeballs send a signal back to your visual cortex located in the back of your brain, they first make a pit stop in the thalamus to get told where to go. In primates and other visually oriented mammals, so cats would apply, dogs would apply, things that are hunters, predators, where they have binocular vision, eyes facing forward, the sense is really important. They get this layered effect. So where did my thing go? So you see how there are layers, and it's like 50-50. So if I go to the next one, you'll actually see, I think that one's unclear. Let's look at it this way. This is ipsilateral. No, I'm sorry. This is contralateral, and it's your nasal vision stuff that you see in your periphery, because it actually crosses the chiasm and it goes to layers 1, 4, and 6, like segregates out like that. And so on the other side, your contralateral vision again goes to layers 1, 4, and 6, but in the other hemisphere. And then the ipsilateral side is your central vision, because think about it, rays of light that are coming in and hitting the outside of your retina, and that's staying, whereas stuff outside of your vision, peripheral stuff, is going and hitting your kind of nasal area retina, and that crosses over, which is why when you get a concussion or something, it actually presses down on your brain, gets a little swelling, presses down. The chiasm, you can essentially say, is cut off completely, which means you only see a tunnel. So if ever you were wondering what tunnel vision was, that's it. So here's another elegant drawing of how that works. And so you can unpin me, go back to Nolan, and then if you guys are interested, because we're running a little late, but if you're interested, I can show you how the pharmacology works. That might be interesting to you. Go ahead, Nolan.
Okay. Just trying to get this back up. Okay. All right. Okay. Stop blink.
It is. It's animated though, isn't it?
Is it?
It's supposed to be. Hold on.
Okay.
Yeah,
okay,
it
got
should. It should be. Yeah, because I'm looking at it on my screen. Yeah, it should be fine.
Good. Okay. So the full inhibition of activity in the fellow eye, which would be like the injected one caused by tetrodotoxin, did allow for the successful recovery of the amblyopic eyes in mice and cats after their traditional critical period for recovery had passed. I know we kind of established that critical period may not really be a thing. This method of treatment could be viable in humans. On the mice and cats, there was success. Cats have similar visual systems to humans, and the point was that they wanted to try a treatment in two species for that purpose, because some previous things that have been tried aren't effective in more than just mice or rats, for instance. And then there may be more potential for brain plasticity than previously thought. I mean, especially what Dr. Char was talking about how it's not really a critical period. It's just if you treat it differently, then you can change the brain indefinitely. And so in terms of using TTX, I'm not sure whether that could really be expanded into other parts of the brain as effectively as in this situation. But it does kind of just give the implication that, there's more than we know out there.
I would have said that was a crazy idea to begin with, but how long has Botox been on the market? And it works in not quite the same way, but it's same idea, right? And we use Botox. We inject ourselves with botulism all the time, and it works really well for things like migraines and wrinkles, stuff that matters. Oh. Okay. Anything else? Freshmen, there will be a quiz on this tomorrow morning. So I hope you understood everything he said. There really won't be, but I do want to get your feedback tomorrow on it. So Nolan, should this have been published in eLife? It's one of the sexy journals.
I think it did deserve to. I think there were some things I didn't like about it. I talked maybe too much about like the 4 to 5 cats thing. But I mean, I feel like clarification would have been good. And then also, I felt like one of the big selling points for this paper that like they kept on talking about in the introduction was like, oh, this provides long-term recovery. And then they only, kept recording up to a month. And a month is longer term than what the reverse occlusion did.
True.
But I would have liked to see, maybe a little bit longer, because I feel confident that this could, remain effective, but I feel like this is not totally conclusive. However, it is, a significant advancement. I feel like, it definitely is, interesting. So, and I think it was generally good. So I think it did deserve to be in eLife.
Okay. Can you stop sharing your screen?
Yes.
Okay. So anybody have any questions? Campbell does.
So I don't understand. So like, why did they suture the mice's like eyes shut? Could they have just like done that differently?
Sure. They could do it differently, but it's not. It's more messy to do it otherwise.
Like, what could they have done instead?
Funny you should ask. They could have done this. In this paper, the mice had contact lenses, black opaque contact lenses that were stuck in their eyes. Now you can't see those. This is their LGN, but you could do it that way. Most of the time, when people are just checking like the input of monocular vision, they remove one of the retinas. They remove.
Can't they just like give them like eye patches though?
The mice are heavy groomers. They will take them off. Really? Yes. Oh. Because that's what they do, and they'll do this on their hair because they have hair, and they'll do that a lot. And what's everything's connected. Okay, that behavior is driven by serotonin being released onto 5-HT, 5-HT 5A and 2C receptors, I think they're called. Serotonin is also the thing that is used for obsessive compulsive disorder. So we actually use that grooming behavior as a measure of obsessive compulsive disorder in mice, and for pruning. So if you were wondering, if we look at for a moment, let me go back to the paper. If we look at this paper for a second, and you look at here, 8 in H, what does the LGN look like? It is not as striated and delineated as it should be, like you saw when I showed you the slides of the primate one, where it's layers, right? Layers 1, 2, 3, 4, 5, 6. Instead, it kind of looks like a mishmash, because when they don't receive stimulation, they don't prune correctly. And the reason they don't prune correctly is because they are being inhibited. Oh, shoot. I was supposed to hit transition. Sorry. This one here, you don't really see over here, right? That these are, those should be much more defined than they are. And so if you use a mouse as an example, the top one, the top A and B, the very top row, that's how LGN should look in a mouse. Most of the LGN, the black stuff, let me go back to, where is it? The black stuff up here, okay? This is the contralateral input because most of mouse vision is contralateral with this little tiny ipsilateral part. But if you start screwing up their serotonergic system by giving them antidepressants or anything like that, they end up not being able to prune it out, which is why sometimes you see young people with learning disabilities have really thick Coke bottle glasses, especially people who have autism, because one of the treatments that we give kids is antidepressants. And antidepressants screw up their vision permanently because their early childhood is a critical period. So Nolan's presentation would suggest from the Bear Lab that maybe these kids have a chance if we start actually manipulating what they can see from an early age to counteract what happened with the pharmacology. Okay, I see yawns, so people don't find that as interesting as I do. If you use other drugs, you will get similar things, like, I don't know, cocaine. Okay, I just thought I'd throw that in there because everybody likes cocaine. Okay, no further questions. Everybody's good. Okay, thank you very much. Good job, Nolan. We need to come up with a better way than the silent clapping that happens. We should have some sort of, some sort of like a salute or something. Be like, that's our clap for you, or I don't know. Oh, look, Miss Hughes is here. I knew there was something evil in the room. There it is. We found it. All right. Thank you, everyone. Good night. All right. See you guys later. Make sure you're in dress code tomorrow.
Thank you.
Bye.
Thank you.
Good job, Nolan.
Thanks. It was okay.
Not okay. No, it was great. That was very, very good. Very thorough.
Okay, thank you.
Better than usual. So that was I appreciate that. Yeah. Thank you.
All right, good night. Thank you.
All right. Mary, let's